Hi everyone, I'm Furkan, and welcome back to the Game Engine Development Series. In today's video, we'll be diving into how 3D shapes are projected onto a 2D canvas, and we'll also be drawing our very first triangle. If you haven't seen it already, we created a canvas as a GLFW window in the previous video, so feel free to watch that first. Otherwise, let's get started. A simple game scene can be constructed by a visual observer with an object being observed. We can start by defining the visual observer as a camera, with its position, looking direction and field of view. Imagine we have a cube in front of our camera. Each point of the cube has a projected position on the canvas. By calculating all these projected positions in the scene and connecting them with lines, we create the outlines of what the camera sees. This process of transforming a point's position from world space to screen space is achieved through a series of matrix multiplications. We use 4x4 matrices for each transformation unit. The view matrix is constructed using the camera's position and viewing direction, while the projection matrix is built using the field of view, aspect ratio, and clipping planes. First, the world position is multiplied by the view matrix to translate it into view space. Then the view position is multiplied by the projection matrix to translate it into screen space. Before calculating the screen space positions, we must initiate a draw call. For example, to draw a triangle, a single draw call is needed. But before executing any draw call, the necessary data must be sent to the GPU memory. For example, a single triangle requires a vertex list of 3 points, along with an index list that specifies which of those points form the triangle. With an index list, we can reuse the same points with multiple triangles. For example, a quad, which is a square, requires 4 points and 6 indexes that describe 2 triangles with reusing 2 points in both of them. Sending this data to the GPU done once if the object is not changing its shape during its lifetime. However, we can still perform simple transformations, such as changing position, orientation, or scale, without modifying the object's internal data. These transformations are handled by a model matrix, which transforms a point's position from local space to world space. The first part of the implementation is defining the triangle and sending the data to the GPU. In the createTriangle function, first, we create an array that holds the position of the triangle's vertices and their corresponding colors. Each vertex has 6 components. The first 3 represent the position, and the next 3 define the color. We also define an array of indices that tells OpenGL how to connect the vertices to form a triangle. Next, we generate 3 OpenGL objects. The vertex array object to store the configuration for the triangle, the vertex buffer object to upload the vertex data to the GPU, the element buffer object to upload the index data, specifying which vertices make up the triangle. We bind the vertex array object first to start recording its state. Then we bind the vertex buffer object and send the vertex data to the GPU. Similarly, we bind the element buffer object and upload the index data. These buffers ensure that all the triangle's data is stored on the GPU for fast rendering. The next step is to set up the vertex attributes. This tells OpenGL how to interpret the vertex data. First, we use the glVertexAttrib_pointer function to define the layout of the vertex attributes. Attribute 0 stores the vertex position x, y, and z, starting at an offset of 0. Attribute 1 stores the vertex color, red, green, and blue, with an offset of 3 floats as it follows the position data. Each vertex has a stride of 6 floats, combining position and color. After defining these attributes, we enable them, and finally, we unbind the vertex buffer and vertex array objects to complete the setup. Now, we're going to use a shader program to implement a transformation chain for the positions of the points that make up the shapes to be drawn, and then paint the canvas. A simple shader program is constructed by 2 functions that run in the GPU, which are vertex shader and fragment shader. They are written and executed together, but they are fundamentally different. For a single draw call for a triangle, a vertex shader runs for 3 times. The purpose of the vertex shader is outputting the screen space positions of the input points. From the vertex shader, we can access the data that we sent to the GPU as vertex attributes. These attributes are tied to each point in the mesh. We also use uniform variables that stay the same for the whole mesh. For example, transformation matrices. After the vertex shader function executes, it determines the positions of 3 points on the screen. Then the fragment shader takes over, running for every pixel that falls within the area covered by this triangle. The fragment shader outputs a color for each pixel, painting the canvas. Variables sent from the vertex shader to the fragment shader are interpolated based on the pixel's position, relative to the triangle's vertices. For example, sending red, green, and blue values for the triangle's vertices creates a smooth gradient across the area. Let's walk through the remaining steps to complete the implementation. First, we set up the shader program by reading the shader files, which is handled by the shader and file manager classes I created. These are simple, and you can check them out. Next, we grab the screen dimensions for perspective calculations. For the camera setup, we place it at a position of 2 on the Z-axis and make it look toward the negative Z-axis. Then, we define 3 transformation matrices: the model matrix for object transformation, the view matrix to position the camera, and the projection matrix to manage the perspective view. In the main loop, we activate the shader program using the use function, update the model matrix, and pass all transformation matrices to the shader. We bind the vertex array object and issue the draw call to OpenGL to draw the triangle using the vertices in the element buffer. Now for the shaders, the vertex shader takes the vertex position and color as inputs. These inputs correspond to the attribute layout locations we set earlier. It also declares the model, view, and projection matrices as uniform variables. The main function combines these matrices with the vertex position, transforming the triangle from local space to screen space. The vertex color is passed to the fragment shader for interpolation. The fragment shader receives the interpolated color and outputs the final pixel color. It converts the color to include an alpha value for transparency, which we set to fully opaque. Returning to the main loop, we clean up by unbinding the vertex array object. Before running the program, a few adjustments are necessary. Add the GLM library to the Conan file and the CMakeLists file. Update the CMakeLists file to include all source and header files from the source directory. Finally, add a CMake command to copy the shader files into the build directory, as they are read and compiled at runtime by our program. After these updates, running the program should display a triangle with smoothly interpolated colors. Additionally, the triangle rotates as the model matrix is updated in the loop. This marks the 3rd milestone of our project. Congratulations! Now don't worry if some concepts still feel a bit unclear. That's completely normal. Mastering these computer graphics fundamentals takes time and practice, but seeing your code come to life on screen makes it all worth it. If you're excited about learning these technical concepts and building your problem-solving skills, you'll want to check out today's sponsor, Brilliant. Brilliant offers interactive lessons in math, data analysis, programming, and AI, helping you grasp complex concepts through hands-on learning. You're actively engaging with the material. It's about thinking critically and finding creative solutions. Content is crafted by experts from institutions like MIT and Google. Brilliant makes learning a habit. With just a few minutes daily, you can consistently improve your skills. One standout course is Vectors. You'll master vector operations, scaling, transformations, polar coordinates, and dot product. These principles are crucial for understanding motion and physics in digital environments. You can try everything Brilliant has to offer for free for a full 30 days. Just head over to brilliant.org/fusarihan or click the link in the description, or you scan the QR code to get started. You'll also get 20% off annual premium subscription. So, we've learned how to define a mesh, send it to the GPU, and use this data to render the mesh with a shader program. The project code is available on GitHub. If you have any questions or encounter problems, please start an issue or discussion there. Also, let me know in the comments what could be done better in this video. I'd love to hear your feedback. Next time, we speed up the process and dive into reading 3D model files and rendering them with textures. Don't forget to subscribe so you don't miss it. Thanks for watching. I'll see you in the next video.